I'm going to take you through several different examples of delta epsilon proofs, but first I want to spend just a little bit of time with the definition. First of all, depending on where you learned the delta epsilon proofs, you may not be familiar with these symbols. So this upside down A means for every. So that's going to be a given value for every epsilon greater than 0. And then our backwards E here means there exists. So there exists. That means we are going to be finding this. So there exists. Let's see. And then such that I don't think I have any other symbols. This one right here is an implication symbol. So this means leads to. It's a conditional statement. We can also put an if in front and a then in the middle there. So that's our conditional statement. With this definition, we're going to be starting with this statement and then showing that logically, mathematically, we can get to this statement. Okay, so now the epsilon and the delta. What I want you to remember with the epsilon and the delta is how they are tied together. So we have that f and x, so f of x and L are y values, and those are tied together right here, and we can see that the change in the y direction is defined by this epsilon. So that epsilon is going to be the difference or the distance away from L. And then similarly, if we look at the x direction, so in this x direction, I've got delta. So we've got delta here, which is limiting that distance between x and the value that we are approaching, c. So we can think of this as this tolerance or error or change in the x direction. Our goal is to show that they're linked. As we shrink down the value delta, it also shrinks down that distance, and we end up approaching our limit L. Let's get into some of these proofs. Now I'm going to be covering linear proofs only, so x to the first degree. I also have a video with quadratics with x to the second degree. So if you're looking for those, take a look at my description down below. Let's go ahead and dive in. As we're putting our work together, the first thing that we need to do is to identify what our values c, f of x, and L are for this problem. C is the value that x is approaching. F of x is that function, so that's going to be 5x plus 1, and L is our answer, the answer to that limit, and that's going to be 11. In our work, we're going to put both the delta statement and the epsilon statement together. Our end goal is really to find delta in terms of epsilon. So that's what we want to do. That's our main goal there, if you can read my writing, delta in terms of epsilon. Let's go ahead and start with the delta statement. So this is 0 less than x minus c, but c is 2, less than delta. We also need our epsilon statement. So the epsilon statement is this f of x minus L. Well, f of x is 5x plus 1. Minus 11, this is an absolute value, it's a distance, is less than epsilon. We are going to continue working with that epsilon statement so that we can get delta. So watch what I do. I'm going to work through the math here, just simplifying what I have on the inside. So that's going to give me 5x plus 1 minus 11. This is minus 10. Is less than epsilon. I can factor a 5 out in front of the absolute value bars. So 5x minus 2 is less than epsilon. And take a look at what I've got. I have what I have up here in my delta statement. So I can go ahead and replace delta there, and I end up with 5 delta is less than epsilon, and we have that delta is related to epsilon by epsilon over 5. We know we need it to be less than epsilon over 5, so we can go ahead and let it be as big as epsilon fifths. So we are going to choose delta to be epsilon divided by 5. Now, it is no coincidence that 5 happens to be the lead coefficient. We're going to use that fact in the next couple of examples. It's going to save us just a little bit of time. Now let's work on the proof. The proof is really our answer, and we need to make sure that we are following our definition very, very carefully, only assuming what we can. So first of all, for every epsilon greater than 0, we are going to say that we are given an epsilon greater than 0. It says there exists a delta greater than 0. We've chosen it, so we are going to say choose delta equal to epsilon over 5. We needed that to be greater than 0. Epsilon is greater than 0, so I know that this one is greater than 0 as well. As I'm working through my proof, I need to show that I can start with the delta statement and work my way to the epsilon statement. So I'm going to start with that delta statement. So in terms of my problem, so I really need this statement now. So I'm going to say for 0 less than x minus 2 less than delta. I can go ahead and replace delta with epsilon fifths, and I can drop off the greater than 0 there. We just don't want it to be at 2. That's why we need it to be greater than 0. So absolute value x minus 2 is less than delta, which is epsilon fifths. Let's multiply both sides by 5. So when I multiply both sides by 5, I'm just going to do the math so you can see here, but you do not need to write that step. We're going to say that 5x minus 2 is less than epsilon. What I am doing now is I'm working backwards through my steps. I am at this step over here, and I'm going to work my way backwards to my epsilon statement. So let's just keep doing the math here. I'm going to bring that 5 through, and I get 5x minus 10. So that's this statement right here. So check, check. So I know that that's going to be equal to this statement right here. So I'm just going to write that out. Equals, so we have to rewrite this so that it's in the proper form. 5x plus 1 minus 11, absolute value is less than epsilon. We have done it. We have shown that our delta statement, so limiting the distance between x and c by delta, leads me to also limiting the distance between my function and the limit. So I can say, therefore, I need just a little more room for my conclusion here. In my conclusion, I like to write therefore as the 3 dots in a triangle, but you can write out therefore as well. And I'm going to go ahead and write what I just showed. So 0 less than absolute value x minus 2 less than delta did in fact lead us to our epsilon statement of f of x. So 5x plus 1 minus 11 less than epsilon, and we just proved that that limit as x approaches 2 of 5x plus 1 does equal 11, and that's the end of our proof. So what I've got over here on the right hand side, all of this is the answer, kind of like writing an essay. So all of that is the answer. Everything over here was just our scratch work. When we get there, here comes our next example. So in this example, we're going to prove that the limit as x approaches 3 of 2x equals 6. So I've got this set up, but we're going to have our work over here on the right, and then our actual proof, our answer is going to be over here on the left. I'm not going to write out the entire limit definition, but what I am going to write out are the statements that we're looking for. So we need our delta statement, so x minus c less than delta, to lead us to the epsilon statement. So f of x minus L less than epsilon. Let's go ahead and identify what everybody is. We need c. c is equal to 3. My function is 2x, and L is equal to 6. As I'm doing the work, I first need delta in terms of epsilon. That's really my goal here, and I know it right off the bat. I know that my x's all get multiplied by 2, just like in the last example, all of those inputs, all of those x's got multiplied by 5. So I know right off the bat here that delta is going to be epsilon divided by the lead coefficient. This works for linear functions only, so epsilon divided by 2. So all I really need then in this work are the delta and epsilon statements. Let's go ahead and put those together. So my delta statement, 0 is less than, I'm right here, x minus c, that's going to be x minus 3 is less than delta. And then my epsilon statement, so that's going to be f of x, which is 2x, minus 6 is less than epsilon. Let's go ahead and work this backwards and make sure that we can get ourselves to the delta statement because we're going to need that in our proof. Doing just a little bit of math here, I can pull the 2 out in front of my epsilon statement. So 2x minus 3, perfect, is less than epsilon. And this right here is delta. So I'm ready to do my proof. So here comes my proof. In my proof, I am going to be much more formal, and I say, given I need any epsilon greater than 0, there exists. So we have chosen, so we're going to choose delta to be epsilon divided by that lead coefficient 2, which makes it automatically greater than 0. And then we go into our statement right here. This is really where the work is. So I'm going to say for 0 less than, and I am going to write it here in terms of our problem, x minus 3 less than delta, but we've got delta as epsilon over 2. I can drop the 0, so x minus 3 is less than epsilon divided by 2. Now I'm doing the math to show that I can end up at my epsilon statement. Let's multiply the 2 in, so I get 2x minus 3 is less than epsilon. If I multiply that 2 through, I end up with 2x minus 6 is less than epsilon, and I think I am there. 2x minus 6 is less than epsilon. So that's exactly what we were looking for. This is f of x minus L. You don't need what I've got in pink written in there, but we are finished. We just need our conclusion. So like an essay, I need my introduction. So here's my introduction. I need the body, and then I need my conclusion, which is what I'm doing now. So I'm going to say, therefore, I like to put the statement that I just proved, 0 less than x minus 3 less than epsilon did lead me logically to 2x minus 6 being less than epsilon. And I can say, and we just showed that the limit as x approaches 3 of 2x is in fact 6. Okay, I hope these are getting a little bit easier for you. Let's do another example. Here's our next example. So we want to prove that the limit as x approaches 2 of 3x minus 2 is in fact equal to 4. Now, if you are feeling good about things, go ahead and pause the video, see how far you can get through this. At the very least, can you figure out what delta is in terms of epsilon based on that function? So if you're going to pause the video, come back and I'll see you in a minute. Otherwise, go ahead and follow along with me. I'm going to put what we need from the definition up here, and that's our delta and epsilon statements. So 0 less than absolute value x minus c, so the distance between x and c is less than delta, implies that, or leads us to, f of x minus L less than epsilon. So let's identify what each of our values are. So c is equal to 2, f of x is that 3x minus 2, and L is equal to 4. I divided our page up here so that we've got space to do our work and space for the actual proof. Let's go ahead and start with the work. I want to start with delta in terms of epsilon. Delta is an x value. Every x value in this function gets multiplied by 3. there happens to be a -2, but the key is that they are tied with that multiply by 3. So that means that delta is going to be equal to epsilon divided by 3 when we put our proof together. We also want our delta and epsilon statement, starting with that delta statement. So 0 less than x minus c, so that's x minus 2, is less than delta. And then let's also put together our epsilon statement. So f of x, which is 3x minus 2, minus L, so minus 4, is less than epsilon. We're going to do the work so that we can get to the x minus 2. And the work is just working through some algebra here. So I've got 3x minus 2 minus 4. That's 3x minus 6. I can pull a 3 out in front, so this is going to be 3x minus 2 is less than epsilon, and we've got where that delta is living. Let's go ahead and dive into the proof. So as we work through that proof, we start the same exact way every single time. So given any epsilon greater than 0, we are going to choose our delta. So we're going to choose that delta is equal to, because of the lead coefficient, epsilon divided by 3, which automatically makes delta also greater than 0. Now for our conditional statement. We've got our delta statement, 0 less than x minus c. Well, I'm working with this statement right here now, so that's x minus 2 is less than delta. We've already established that delta is epsilon divided by 3. So we can rewrite this as x minus 2 is less than epsilon thirds. Let's multiply both sides by 3, and I get 3x minus 2 is less than epsilon. Now I am doing the math and I'm working this guy backwards. So as I'm doing this math here, let's multiply that 3 through, and we end up with 3x minus 6. So 3x minus 6 is less than epsilon. So there's our 3x minus 6. Going up one level, I can rewrite that now as parenthesis 3x minus 2. I'm right here, 3x minus 2 minus 4 outside the parentheses is less than epsilon. Now, you don't need to write what I've got in pink here, but just to show you what we did, we just showed that this is linked to the distance between my function value and L. I'm approaching that limit. Here comes our conclusion. So therefore, we were able to take the delta statement, so 0 less than x minus 2 less than delta, did in fact lead us to the epsilon statement, so limiting the distance in the y direction as well, less than epsilon, and the limit as x approaches 2, that's an x approaches 2, of f of x, 3x minus 2, is in fact equal to 4. Okay, we've got one last example. You guys are doing so well. So I went ahead and gave us two different sections. On the right-hand side, our work. On the left-hand side, the proof. I'm going to go through this one a lot more quickly, but we're still going to do the work on the right-hand side here. Now, first of all, you should be able to identify pretty quickly what we need to choose for our delta. Delta is going to be epsilon divided by 4 because of that lead coefficient 4. What we need next are the delta statement and the epsilon statements. I'm going to put those along in our work. So I've got 0 less than x minus c. X is approaching 0, so c is equal to 0. And that is less than delta. I can actually clean that guy all the way up to just absolute value x is less than delta. I also need my epsilon statement. So my function is 4x minus 1. So 4x minus 1, and our limit is -1. So minus -1 is less than epsilon. Now I know in my proof I'm going to need to work from this statement, so I'm going to continue cleaning this guy up. So as I continue to clean this up, I get 4x minus 1 plus 1 is less than, these are 1s, and that's absolute value is less than epsilon. So we get 4x is less than epsilon, and there is our absolute value of x less than epsilon. epsilon, and this absolute value of x right here matches with the absolute value of x right there. We are ready for our proof. Now you've noticed I've been really consistent in my language for the proof. I do recommend that you stick as closely as you can to the same script. It just makes life a lot easier. So here we go. So I'm going to go ahead and say that given, so really we're given any epsilon greater than 0, we are going to choose, here's a place where you could put let, I'm going to use choose though, choose delta to be epsilon divided by 4, which automatically makes this greater than 0. Now I'm ready for my delta statement. So I can say for 0 less than, I am right over here in my work. So 0 less than, I'm going to write it out as x minus 0 is less than delta. But I can clean that up and replace delta with what we've chosen here, the epsilon divided by 4. I'm going to work through the math. So I've got 4, absolute value x is less than epsilon. And as I'm working my way back up, I'm at this statement right here, and I'm going to work my way up the chain. So I need to bring the 4 on the inside. So absolute value for x. So that takes care of this statement here. And now I'm ready for this guy. So let's go ahead and rewrite that as parenthesis 4x minus 1, this plus 1, I can just skip right to this statement here and write this as minus negative 1, absolute value less than epsilon. This is our epsilon statement, so we did it. I am ready for my conclusion. I can actually shortcut my conclusion depending on whatever your teacher requires. I can just write the limit statement as my conclusion. That's really what our conclusion is here. So I can say that the limit as x approaches 0 of our function for x minus 1 is in fact equal to negative 1. You are doing so well. If you're able to follow me, you have learned a ton while you've watched this video. Keep on practicing. Now I've got a video also for limits of quadratic functions using the Delta Epsilon proof. So take a look at that video. I'll also post it down below. Good luck everybody, and thanks so much for watching.